All right, bro. Welcome to the most jacked up academics you're ever going to get. This is Paint on my laptop, and I'm doing a screen recording. So, anything in balance is going to be the balance of forces, right? So, in the case where you got a body being orbited by another body, the forces between the two are going to be in balance. If they weren't, then our little astronaut friend would eventually work his way to terra firma, or our astronaut friend would be on his way to Saturn, floating forever like Frank Poole in 2001 Space Odyssey. So, let me get rid of that. So the forces have to be in balance. So the two forces really that we're talking about here is, hold up. Say this is going to be jacked. Let's try this. There we go. So you have two forces in balance. One is force due to gravity, and the other force is centripetal force, if you want to call it that. And it's really not a force per se. It simply says that a body that's in motion or in a given velocity wants to remain in that velocity. And it may very well be zero velocity, or it could be 10 million miles an hour. And it will remain at such velocity until acted on by an external force. So we kind of label it centrifugal force, and that's as this thing curves around the Earth, there's a force pulling on it outward, and that's really just the desire of this object to travel in a straight line. Because that's what it wants to do. But since it's not, that tells us there's a force acting on it. But the point is, we got two forces that are in balance here, and that's what is important in this discussion. So let's talk about those two forces. One of them is the force due to gravity, and that is, this is going to be painful to watch. It's force due to gravity is equal to capital G M1 M2 divided by d squared. And all this says is the force due to gravity between object 1 and object 2, these are their two masses, mass of object 1, mass of object 2, multiplied times the gravitational constant, which is 6.67, times 10 to the negative 11th. For this discussion, my brother, that's close enough to zero. We can take that out. And then, of course, Newton figured out all this stuff. We divide all this by the distance squared between the two objects, and that's the force due to gravity between these two objects. Force due to centrifugal force is equal to the mass of the object moving, i.e., if we're going to call this the satellite, we'll call this the Earth, so we'll do M sub E for Earth. Well, the mass of the object times its velocity squared times the radius of the circle that it's going around and round and round. So we just said these have to be in balance. See our equation over here. So this means the mass of the Earth, this is going to be painful, times the mass of the object divided by d squared, i.e. force due to gravity, has to be equal, because remember this is a thing in a stable orbit, has to be equal to the mass of the object times its velocity squared times the radius of the orbit. Of course, this is all over 1, right? This is over 1 as well. If we wanted to make this look pretty, a fraction equals a fraction. But notice here, anytime you have something on one side of the equation and it's also on the other side of the equation, remember we can cancel those out by multiplying both sides by the inverse of whatever that is. So we'll do the same over here. And now the mass of the object, i.e. our astronaut, cancels out on all sides of the equation. And what we're left with then is the following. Well, these cancel out. Just yanking them out of here. So now we're left with this equation here, and I'll get rid of this little fractional thing over 1 just to make it look normal. Let me move this guy down here just to make it look normal. So really what we're left with is the forces between the two are equivalent to the mass of the Earth divided by the distance squared between the two objects. But notice we have velocity squared and r, which is the distance from the center of the Earth. That's also this distance from the center of the Earth. This d and r are the same terms. They're labeled different. So let's make them the same term. In other words, this is really a d, or we could have made this r squared. It doesn't matter. Notice now we can cancel that out and leave just a single d to the first power over here, which is the same as just d. So let's take that guy out. Now we're left with this. Let me take him out of here. So now we're left with the following. And I'll redraw this for clarity. We're left with the mass of the Earth divided by the distance is equal to the velocity squared. And of course, the velocity squared of the object in motion. And this is your general orbital equation. So in other words, the mass of the object does not matter. It could be 1 kilogram or 8 billion kilograms. It will get canceled out in our formula. So the only variables then involved here would be if the mass of the Earth changed, and it actually does over time, about 6,000 tons a day from space dust and debris, things like that. I read that in a factoid book one time when I was about 7 or 8, I think. So, but for purposes of our discussion, it remains a constant. It remains a constant. But what can change is our orbital altitude from the center of the Earth. We always think altitude in terms of distance above the ground, but in reality, the formulas involve the distance from the center of the Earth. And then the velocity. So let's take a look at what this is like. On any time you have a fraction, when the denominator goes up, the overall equation goes down. And this, therefore, has to go down if this equal sign is going to stay there. So in other words, if our orbital distance, in other words, our orbital altitude goes up, our velocity is allowed to go down. Conversely, if we want our orbital velocity to go down, then I have to raise the orbital altitude. A great example, a geostationary satellite. I want it to stay over New Mexico. Well, New Mexico rotates once every 24 hours, so my satellite has to rotate only once every 24 hours. Well, brother, that's a slow orbit. That's not very fast. So I really have to bring this velocity down to stay over New Mexico. Therefore, I have to raise its orbital altitude quite a bit. In fact, we call that a geosynchronous orbit. And those orbits are up at 24,000 miles instead of, for example, the space station, which is down in low Earth orbit, about 120, 130 miles. And of course, it's hauling ass at 17,000 miles an hour. We don't want the international, let me get rid of this stuff for readability. We don't want the International Space Station to be up at 23,000 miles in its orbit. You know how expensive that would be to bring anything there? We want it in as low orbit as possible so as not to collide with air molecules, because those collisions will slow down its velocity. And guess what? The thing will have a decaying orbit. So we want to put it high enough to stay out of the atmosphere, but we want it close enough so we can get to the damn thing. So in other words, we want D to be small as possible. Well, in a fraction, when your denominator goes down, the overall fraction goes up. And when this side of the equation goes up, this side of the equation has to go up. So when NASA says, oh, I want the International Space Shuttle to be in a low Earth orbit, then the engineers say, all right, sir, we're going to have to make it haul ass. And of course it does. So, but the bottom line, the whole purpose of this was to show you that in orbital mechanics, the mass of the object orbiting makes no difference. Makes no difference. By the way, on a side discussion, I won't do all the math behind this either, but if you and I were to be on the moon or on the Earth in a vacuum chamber and drop two objects of greatly different masses, a golf ball in one hand and a bowling ball in the other, they both would strike the Earth at the same time. Well, how can that be if the force of gravity is dependent between the mass of the Earth and the mass of the two objects falling? Because it doesn't have much to do with the mass of the object falling. It has to do with acceleration due to Earth's gravity. And if you run the math, just like here, the mass of the object falling zeroes out of the equation, and all you're left is the mass of the Earth. And it's interesting because if you really understand orbital mechanics, you'll actually understand that the object in orbit is actually in continuous free fall. It is falling towards the Earth, but it also has a lateral velocity great enough that it misses the Earth. If I throw a baseball at 90 miles an hour, it'll go 100 feet and hit the Earth because the Earth pulls it down with a curve that is sharper than the curvature of the Earth. So it collides with the surface of the Earth. But if I throw that baseball at 19,000 miles an hour, yeah, the Earth pulls on it, but it's got a forward enough velocity that it will miss the Earth during its entire time around. And that is the basics of orbital mechanics in terms of two-body orbital mechanics. So I hear Connor coming in. We're going to go grab a beer, but I hope this was useful. All right, I'll talk to you soon. Bye.